Good evening. Today we are going to deal with topic 1, the section on numbers. One of the first sections on numbers is recurring decimals. The concept of recurring decimals is tested quite often in the level 2 curriculum. It is wise that learners get to understand how to go about converting and doing and working with the recurring decimals. There are many ways to convert a fraction into a decimal. The obvious and the quickest way is to use a calculator. Living in an age where we are today, learners often use calculators. With the advanced calculators that you do have, it becomes quite easy to do something like this. But obviously, we want to see whether a learner can perform this mathematically. For example, if we take a fraction 5 over 16, and this is a fraction where the 5 is the numerator and the 16 is the denominator. 5 over 16 is a fraction. If you key in 5 over 16 on your calculator by pressing 5 divided by 16, you end up with an answer of 0,3125. 0,3125. This answer stops. 0,3215 or 3125, and that is it. It does not go further. This is a terminating decimal. Terminating. The word terminate means to come to an end. Consider the next example. 6 divided by 11. If we take 6 divided by 11 and plug them into the calculator, you would end up with an answer of 0,545454. And you would notice that this 5 and the 4 continues. Obviously dependent on the type of calculator that you are using. It will continue on and on and on. These 3 dots over here signifies that the 5 and the 4 continues to infinity. This, dear learners, is known as a recurring decimal. We have now seen the difference between a terminating and a recurring decimal. All recurring and terminating decimals can be written as exact fractions. Exact fractions. All terminating and recurring decimals can be written as exact fractions. Let us now go further and look at the definition. And watch this. A decimal is said to recur if the digits after the comma repeat infinitely, or basically repeats to infinity, meaning repeats on and on and on. All fractions written as decimals will either be terminating or it could be recurring. If a decimal is non-terminating or recurring, then it cannot be written as a fraction if it is non-terminating or non-recurring. And obviously, this is something you have already done. These are irrational numbers. 2 examples of irrational numbers are root 2 and pi. Let us start by further investigating this by using our calculators. Guys, I need for you to take out your calculators and follow as we go along. We will go a bit slowly at first so you can understand exactly where we are going with this. On your calculators, I want you to key in the following problem. Press 1 divided by 3. I know this is easy, but we still want to show a point. 1 divided by 3. 1 divided by 3, if I have to press on this calculator, it's 1 divided by 3 is equal to, and I end up with an answer of 0,33333, and you would notice that there are many 3's going on here. Obviously your calculator does not go on to so many digits as this one, but it shows you that the 3 recurs. So I end up with an answer of 0,333, and the 3 dots on the right hand side here basically tells me that the 3 recurs. It goes on and on and on. Now this is a bit cumbersome. So somewhere along the way, somebody developed an interesting idea regarding this. And this person went ahead and said, instead of writing 0,3333 recurring, I will now I will invent something, or I will bring about this concept of dot notation. So this person simply went and wrote 0,33333 as 0,3, and they put a dot on top of the 3. This, dear learners, is called dot notation. Dot, I simply put a dot over the 3, and the dot signifies that the 3 recurs, means it goes on and on and on. I think this was a clever idea. Let us try another example. Once again, guys, take out your calculators and do this. 8 divided by 11. 8 divided by 11 gives you an answer of 0,7272727272. The 3 dots indicates that a pattern continues. And if you look at the pattern here, you would distinctly see that it is a 72 that recurs. By using dot notation, this can be written as 0,727272 and on and on and on. Using dot notation can be written as 0,72, where you find there's a dot above the 7 and there is a dot above the 2, basically telling us that it is the 7 and the 2 that continues to recur. 72, 72, 72, continuing. Now guys, this is getting interesting. Let's take a few more. Concentrate. 1 divided by 6. 1 divided by 6, the answer is 0,1666666, 3 dots. The 3 dots again signifies that something recurs. What is recurring? Obviously you can see the 6's. This one, does it recur? No. It is the 6's that recurs. If I have to write this in dot notation, I would get the answer. Yes. 0,16. That dot is only above the 6, telling me that the 6 recurs. Very good. Let's continue. 7 divided by 11. 7 divided by 11 on your calculators gives you an answer of 0,636363. And guys, come on. You give me the answer for this one. In dot notation? Correct. 0,63. There's a dot above the 6. There's a dot above the 3. Those 2 dots tell me, or tells me, that it is the 6 and the 3 that continues to recur. What about this example? 7 or 133 divided by 171. Come on guys, on your calculators. Answer 0,513513513513. And the way I am saying it will automatically give you the answer. What recurs? The 513, the 513, and the 513. Now be careful about this one. If I have to use the logic on the 2 previous examples, I would assume that there will be a dot above the 5, a dot above the 1, and a dot above the 3. But if I do that, it's defeating the purpose of this dot notation and what was intended. The answer here is 0,513, where there is a dot above the 5 and there's another dot above the 3. Any numbers in between the 5 and the 3 will also recur with the 5 and the 3. So this, in expanded notation, will be 0,513, 513, 513, and in dot notation, 0,5, the dot above the 5, the 1, and the dot above the 3. Very good, guys. I hope you're getting this. Let's go further. Write the following recurring decimals in dot notation. 0, 1, 2, 1, 2, 1, 2. If I have to write this in dot notation, what recurs? The 1, the 2, the 1, the 2, the 1, the 2. And your answer is, in 3, 2, 1, your answer 0, 1, 2. The dot above the 1, the dot above the 2. That's good. What about 1, 3, 7, 7, 7? Yes, the 7 recurs. Your answer 1, 3. The dot above the 7 tells me that it is a 7 that recurs. What about this, guys? I'm only doing 0, 0, what about 3, 3, 4, 5, 3, 4, 5? If I have to take an example like this, automatically you will see the 3, 4, 5, the 3, 4, 5 recurs, which means there should be a dot above the 3 and a dot above the 5. Thank you. I hope I'm getting through to you. Next example. There's something long. Obviously, your calculator is not going to give you so many decimal points after the decimal comma. But nonetheless, let's look at this one and see what the answer would be. What recurs? 1, 3, 5, 7, 9. 1, 3, 5, 7, 9. 1, 3, 5, 7, 9. Can you see the pattern? It is the 1, the 3, the 5, the 7, and the 9 that recurs. Where would I put the dots? Obviously not above everything. It will be above the 1, and the next dot will be above the 9, telling me that whatever digits I see from here right up to here, these are the digits that will recur. Thank you. And once again, a reminder, guys, if you need to go back, just simply rewind, go back to the portion that is confusing you, and understand it before you go further. Now let us go further. There's a good one. Worked example number 1. This, by the way, guys, is an example that came out in a previous exam paper. I think the initial ones. It's quite simple. It will be the first example that you would come across. The question reads, convert 0, 2 with the dot above the 2, signifying that the 2 recurs, to the form A over B, where, one more time, convert 0, 2 recurring, which basically means 0, 2, 2, 2, 2, to the form A over B. We understand A over B is a fraction, where, I always say that, this, what in the world is all of this? Now, 99% of the time, when you see something like this, you don't even worry about it. It's very, very important to understand it. One more time. Convert to the form A over B. A is the numerator, B is the denominator. It tells me here, where A, B are elements of integers. What are integers? Integers are whole numbers. Where there's positive or negative, it's fine, but they have to be whole numbers, which means A has to be a whole number, B has to be a whole number. I cannot end up with an answer of 1, 5 over 2. No, both have to be integers. And B must not equal to 0. B not equal to 0. Why have we got that restriction where B must not equal to 0? Obviously, guys, when we're dealing with a fraction, can we divide by 0? Most definitely not. We cannot. So therefore, we will not accept any answers where B is equal to 0. Obviously, it should come that way. But nonetheless, you understand what is being said by this highlighted area. If I have to go about doing an example like this, what I will normally do is, I will write the question in the form of an equation. It's best to work this way. So my first step will be x is equal to 0, 2 recurring. Now why would I want to do that? X is equal to 0, 2 recurring. It simply means that x is equal to 0, 2, 2, 2, 2 recurs. And I'm going to call this equation number 1. When I deal with this conversion, I am going to be dealing with the concept of simultaneous equations. I would want you to do this. Prior to starting of this section, understand simultaneous equations. Go to the video on simultaneous equations, understand it thoroughly, and then come back to understanding how to go about converting recurring decimals to a fraction. Nonetheless, let's go further. X is equal to 0,222 recurring. I call this example number 1. Now guys, I'm going to use a simple concept. I'm going to take the equation and keep multiplying it by 10. Take the equation, multiply it by 10. Once you get two equations, by subtracting one equation from the next equation, ensure that you have an integer as the coefficient of x, and your right hand side is also an integer. Now, in a nutshell, this is what I'm telling you. Take equation number 1. This is equation number 1, which I've created. Multiply it by 10. If I take equation number 1, multiply it by 10, I end up with an answer of x times 10, which is 10x. 0,222 multiplied by 10 equals 2,222. And this, colleagues, learners, I will call equation number 2. One more time, guys. I took equation number 1. I multiplied it by 10. 1x times 10 is 10x. 0,222 times 10 is 2,222. Equation number 1, equation number 2. That's good. Let's continue. Once I've got my equations, I will now try to subtract the equations. In this case, it becomes easy. I simply take equation number 2 minus equation number 1. Now this is what I mean, guys, when I say equation number 2 minus equation number 1. 10x minus x is equal to 9x. 2,222 minus 0,222 is equal to 2. You can see that, and that will cancel away. It's 2 minus 0. So I end up with 9x, which is equal to 2. Where did I get the 9 from? It's the 10 minus the 1. Where did I get the 2 from? It's the 2,222 minus the 0,222. Once I've got 9x is equal to 2, this is a linear equation. Guys, simple. X is equal to 2 over 9, where the 9 is multiplied on the left hand side, comes to the right hand side, and becomes division. Thank you. With this, you should get full marks. Take a moment, guys. Look at this example. Ensure that you understand each step, understand how I got to the answer. Once again, keep multiplying the equations by 10 until such time that you can subtract two equations where the coefficient of x is an integer and the right hand side is also an integer. And there's a nice tip. Use your calculator to ensure that the answer is correct. All you are using your calculator here is to plug in 2 divided by 9 to ensure that you get back to the original question. Thank you, guys. Let's go on now to example number 2. Worked example number 2. Convert 0,24 to the form a over b. If I look at this example, 0,24, the dot is above the 2, the dot is above the 4. Now this makes it a bit more interesting for me. 0,24. If I look at this example, yes, first step, create an equation. X is equal to 0,24. Very good. Write in a form that is much better for us to understand. X is equal to 0,242424. Call this equation number 1. Next step, multiply by 10. Multiply what by 10? Multiply equation number 1 by 10. So equation number 1, which is this equation here, multiplied by 10 will give me, come guys, let's try this. 1x times 10 is 10x. 0,242424 multiplied by 10. The decimal point simply moves one place to the right. Correct. 10x is equal to 2,42424, and it continues. This I will call equation number 2. Now once I've got two equations, my next step, ensure that I will be able to subtract. If I subtract the x's, I get 9x. But if I subtract 2,4242, subtract 0,242424, you will notice that I will not be getting an integer. The moment that you notice that happening, multiply by 10 again. I will take equation number 2 and multiply equation number 2 by 10. Now this is interesting. Some guys might tell you, but why didn't you simply go and multiply by 100 one time? Correct? But I prefer that you keep multiplying by 10. If I multiply equation 2 by 10, I end up with 100x, 10 times 10. 2,42424 multiplied by 10, the decimal point moves one place to the right. I end up with 24,242424. This I will call equation number 3. Now watch what I have over here. If I'm going to deal with something like this, I will say, wait a second, look, after the decimal point, I have a 242424. After the decimal comma, I have a 242424. This and that looks like something that I can subtract, and that's what I want you to look for. Automatically, by looking at that, you would notice that if you take equation number 3, subtract equation number 1, it might give you what you're looking for. Let's check. I've got 100x minus x is not 90, but it's 99x. 24,242424 subtract 0,242424 is the same as saying 24 subtract 0. So I got here 99x, which is equal to 24. Thank you. That seems good. This is a linear equation. I work with the linear equation and I am going to solve for x. If I solve for x, x is equal to 24 divided by 99. And guys, if possible, simplify to the simplest fraction. In this case, the answer is 8 divided by 33. And that's exactly what I'm looking for. This is a very, very good example, guys. I want you to understand this example. I'm going to leave it on here for a minute or so, or less than that, and I want you to understand exactly what is happening in this one. If I have to go about doing an example like this, remember, this was equation number 1, correct. Equation number 2, correct. Equation number 3, correct. 3 minus 1, correct. Get your fraction and get it in the simplified form, correct. Something like this, if possible, 5 marks, 4 marks will be more convenient to use. But remember, between 4 to 5% is something that you cannot lose. Verify the answer by using your calculator. Let's proceed, guys, now to the next example. Worked example number 3. Can you see it's getting a bit more difficult? Convert 0,513 to the form a over b. And if you look at this here, it is 0,513 with the 5 recurs and the 3 recurs. Very good. Let's go ahead. Step number 1, create an equation. X is equal to 0,513. I like this. Step number 2, write it in expanded form. X is equal to 0,513513. It recurs. I'm going to call this equation number 1. Next step, equation number 1, multiply it by, thank you, multiply by 10. Equation number 1 multiplied by 10. Let's start. X multiplied by 10 is 10x. 0,51313 multiplied by 10 means the decimal point moves one place to the right. I end up with 10x, which is equal to 5, 1, 3, 513, 513 recurs. Immediately label this as equation number 2. Next step, I'm going to try to subtract. Automatically, or as you get used to this, you would notice, or you would know when to subtract and when not to subtract. Immediately after the decimal comma is not the same as after the decimal comma up here in equation number 1. Subtraction will not work. The mere fact that subtraction will not work means that you have to multiply by 10 again. Take equation number 2. Multiply by 10. Equation number 2 multiplied by 10. 10x times 10. Correct. 100x. If I multiply this by 10, my decimal point moves one place to the right. I end up with 100x is equal to 51,351,513. Now, as I mentioned before, label this as equation number 3. You are now going to check whether you can subtract. When you check if you can subtract, the digits after the decimal comma must be the same in order to assist you with the subtraction. None of them are the same, which means I have to multiply by 10 again. Cumbersome, I know, but please expect these types of examples. It could come out, it could not come out at the same point, but we'd rather be safe than sorry. Equation number 3 multiplied by 10. I end up here with 100x multiplied by 10, which is 1000x. 51,351,3 continuing here, multiplied by 10. The decimal point moves one place to the right. I end up with 513,513,513. Now, you can notice these digits after the decimal comma are exactly the same as those digits after the decimal comma. Which means if I have to choose any two equations to subtract, obviously it's going to be this equation number 4 minus equation number 1. So let's start. Equation number 4 minus equation number 1. And what do I see here? Equation 4 minus equation number 1. 1000x minus x is equal to, not 990 guys, it is 999x. 513 minus 0 is 513. This is a linear equation, and now you go ahead and solve for x. X is equal to 513 divided by 999. This is a beaut of an example. You would have noticed again when you do your revision, it would have appeared in past exam papers. Nothing stops the same concept from being tested again. May not be the same example, but the same concept. Our last worked example. Worked example number 4. And this, dear learners, is the icing on the cake. An example like this. Recall initially I asked the question, or I made the comment that somebody will tell you, why don't you go and multiply by 100 or multiply by 1000 one time? This example illustrates that point correctly. Start off by saying x is equal to 0,47 where the 7 recurs. Perfect. No marks for this, by the way, guys. Let's go to the next step. X is equal to 0,4777. It's the 7 that recurs. This is example number 1. Happy? Okay, I'm happy. Example number 1 multiplied by 10. I like to multiply by 10. 10x is equal to, the decimal point moves one place to the right, 4,777. Call this equation number 2. Okay, nothing different from what I've done in the past. So you might be saying, but what's so special about this example? Let's continue. We might see what's so special about this. I cannot subtract, so I take equation number 2. I multiply it by 10 again. I end up with 10 times 10, which is 100x. The decimal point moves one place to the right. I end up with 47,777. This I call equation number 3. Now I want to look at the decimal comma. There's my decimal comma. And the digits after the decimal comma. Here you see this 777. I don't see it on the first one, but I see it on the second one. There's it, guys. Now you can see. If I went ahead and I multiplied by 100, I would have not had the second equation. And I would have been confused as to which equation I need to subtract. And now, guys, I can distinctly see equation number 3 minus equation number 2. 100x minus 10, not 999 now, guys. Now it is 90x. 47,777 minus 4,777. Thank you. Ignore these. It's the same as 47 minus 4, which is equal to 43. I solve for x. X is equal to 43 divided by 90. And of course, guys, remember I mentioned to you before, if you can simplify this fraction here, simplify. If you cannot simplify the fraction, you leave it where it is. No problems, you will get the full marks. Now one more time, guys, on this example, why I like this example. Remember, equation number 1 is fine. Multiply by 10 to get equation number 2. I'm happy with that. Multiply by 10 to get equation number 3. I'm happy with that. But now this is the key point here. This is the key point. 3 minus 2. 3 minus 2. 100 minus 10 is 90. 47 minus 4 gives me this 43. And I end up with x, which is equal to 43 over 90. Ponder about this for a moment before I go any further. That's a beauty example, eh? Okay, guys. Time to take a breather? You think so? Let's have a small breather. Okay. Activity: recurring decimals. Guys, I want you to do this activity. Convert the following to the form a over b, where a, b are elements of integers and b is not equal to 0. Take out your writing material together with your pens and you can go ahead. You need to copy down the questions. Okay, there's the 10 examples that I want you to do. Copy them down. Guys, if need be, please press the pause button on your screens. Copy them down. You would have to attempt them first before even going any further. If there is something that you do not understand, you can go to the answer section and get it from there. But do not use the answer section just to be able to complete the work. You are defeating the purpose of this video. I would recommend that you do it. At the end of the day, it is you who needs to understand this work. Let's go to the answers, guys. Example number 1. 0,5 recurring. Guys, I'm not going to spend too much time on this. I've got equation number 1. Multiplied by 10 gives me equation number 2. In this case, it is 2 minus 1. That gave me 9x is equal to 5. And from the 9x is equal to 5, x is equal to 5 over 9. This again is a very, very basic example. If you have made an error, please go back, double check where your error is. We are now going to proceed to question number 2. X is equal to 0,35 recurring. You will notice that the 5 recurs. In this case, I've got example number 1, or equation number 1, times 10, equation number 2, times 10, equation number 3. The trick part here, it's equation number 3 minus equation number 2, where I get a linear equation. I solve for x and you simplify the fraction. Use your pause button again. Perfect. Let's go further. Number 3. 4, 6 are the digits that recur. Equation 1, I was happy with. Equation 1 times 10 gives me equation number 2. Equation 2 times 10 gives me equation number 3. In this case, it is equation 3 minus equation number 1. 99x is equal to 46. And yes, guys, you solve for x. Question number 4. 0,314. You will notice that the 314 recurs exactly like the example that we have done previously. Again, if you are having a problem understanding this, go back to the worked example and work from there. Try the worked example first. Once you understand that 100%, come back to this example. Nonetheless, I had equation 1 multiplied by 10 gave me equation number 2. Multiplied by 10 again, equation number 3. Multiplied by 10 again, equation number 4. Equation 4 minus equation 1 gave me the linear equation, and I solve for x. Somebody will tell you again, because you see 3 digits over here, multiply by 1,000 one time. It would work in this example. If I skip all of the steps, multiply by 1,000, I get equation here. I've got this original equation, it would work out. But remember, the example where it does not. X is equal to 2,3 recurring. It's the 3 that recurs. Equation 1, equation 2, equation 2 minus 1. I get the linear equation and I solve for x. Guys, come on, you should be getting these things correct. There should be no reason why you are struggling with this. Remember your 4 marks. Number 6. There's no difference here except that I'm getting very, very big numbers that I'm working with. Does not change the procedure. Equation 1 times 10. Equation 2 times 10. Equation 3 times 10. Equation 4 minus equation 3. I end up with 900x is equal to 12,111, which, if I solve for x, is the same as 12,111 divided by 900. This, somebody will say, but wait a second, that's an improper fraction. I should go and simplify it. There's no need to. Remember the question. You want this in the form a over b. Is it in the form a over b? It is. The answer can be left as that. Proceeding to example number 7. 1,314, where the 1 and the 4 recurs. Very good, guys. I like this one. Equation 1. Equation 2. You can start marking your work, guys. Check that you have equation number 3. check that you have equation number 4. For the purpose of your exercise, give a mark for each step. Equation 4 minus equation 2. There's 4. There's 2. How do you know to subtract 4 and 2? The numbers after the digits, after the decimal point. Can you see it's exactly the same? And therefore, I get the value for x. And going further, 3 more to go, guys. This is child's play. 4, 4 with the 4 recurs. I'm not even going to explain any further. Answer correct? Thank you. If it is not correct, guys, you should go back. Example number 9, my famous one. X is equal to 0,32 with the 2 recurs. Mark with me. A mark for equation 1. A mark for equation 2. Give yourself a mark for equation 3. Give yourself a mark if you went and said equation 3 minus equation 2. Come guys, give yourself another mark if you said 90x is equal to 29. And last, if you got the answer 29 over 90, give yourself a pat on the back. You are ready for this exams. Okay, jump in the gun a bit, but you are ready for this section. The way that we are aligning marks is not the way that it will be marked in the exam paper. Remember, I told you something like this is about 4 marks. So likelihood that you could be getting half here, maybe a half for this, a half for this, you will get between 3 and 4 marks. Number 10. A good one for the last. This is a long example. Highly unlikely that you will get an example like this in the examinations because it tests recurring decimals, but it's long. We can test recurring decimals using a shorter example. But nonetheless, guys, if you got this one correct, give the friend sitting next to you a tap on his back. The answer that you should be getting, x is equal to 2345 over 9999. I'm going to leave this. Look at the example. Ensure that you have the answer 100% correct. And guys, this brings us to the end of recurring decimals. I hope that you enjoyed this lesson. Just before we leave off, and as you are pondering about that, I want to just go back to one of the slides that didn't work 100% correctly. Thank you guys. Go on to the next lesson.